Hi guys. I just wanted to go over the different topics involving the reactant quotient and the equilibrium constant that we covered yesterday and today, and just give you a chance to kind of look back over this before you go through the homework for before I see you again. So let me just first go over that when we're dealing with our reactant quotient and our equilibrium constant, we're going to be looking at our balance equations, our reactants, going to our products, and then this double arrows representing that idea that we have both the forward and reverse reactions occurring. And just remember that at equilibrium, the rate of this forward reaction is going to be equal to the rate of the reverse reactions. So a lot of the times you can think of this as the double arrows over each other of equal lengths representing those equal rates. One thing when we go to write these expressions is even though we have the reverse reaction occurring, we're always going to treat the species on the left as our reactants and the species on the right as our products for this. So one little thing with this is that our reactant quotient is usually we're looking at it in terms of our initial concentrations. Okay, our concentrations under a specific set of conditions. So we could either have our Kc or our QC or our QP. So whether it's at concentrations or at pressures. And the setup for that, so say I use my concentrations, would just be that my concentrations of my products over the concentrations of my reactants. Okay, and then we talked about in class about how we would be looking at their coefficients and then raising each of the individual products or reactants to that power. For K, this is only used when we are at equilibrium. So say, again, we could have this as Kc or Kp, depending on if we're looking at concentrations or products. So if I set this up based on, in this case, let's say pressures, this would be like the pressure of my product over the pressure of my reactant. Okay, and we'll get into some examples of like in the next one of how that will look with multiple reactants and products and when we have various coefficients. So let me just show you like a basic calculating our equilibrium constant given a set of conditions at equilibrium. So this was an example in the quizzes we had. Here we have our two reactants forming our product here. It says when equilibrium was reached, which allows me to know I'm using Kc. These are my pressures. Kp for this reaction. So if I set up my general equation, I'm going to have the pressure of NOBr, and I'm going to square it based on the coefficient of 2 there. And then I'm going to have the pressure of NO squared over the pressure of Br2. When I looked at the results from the quizzes, I saw that a lot of you guys flip this around. So again, make sure it's always products over reactants. So when we then go ahead and fill this in, you would have your 7.68 squared over our 0.526 ATM squared times the bromine pressure 1.59. Okay, and when you go and you actually plug that in, you should get that value of 134. And just remember that there are no units, okay, when we're dealing with K and Q. Okay, so again, just simple at equilibrium. So we're looking for Kp based on the pressures given at equilibrium to find that value. Okay, now this value is greater than 1, not much greater, but a little bit greater. So keeping in mind that this is products over reactants, that value greater than 1 would indicate that if we didn't have this information, I would expect there to be a higher pressure of my products versus my reactants at equilibrium. So just something to keep in mind. All right, the other big thing we went over is just ways that we would use kind of reference equations in order to find an unknown equilibrium constant for a new reaction. So one thing to start off with is that if I use a combination of 2 or more reactants, I'm going to be taking the product of the individual K or Q values. And most of the time, at this point, we're going to be dealing with Ks when we're looking at combining different reactions. So for like this one here, if I look at this third reaction, okay, I can see it's just the combination of these two. If I cross out my 2 moles of nitrogen monoxide, I get this equation here. So if I'm looking for my Kc3 for this, it's just the combination of the two. This is where you have to be careful. This is different than when we did our enthalpy values in terms of Hess's law, where we added them. Here we're going to multiply them and get the product. So this would be my Kc1 times my Kc2, which when you actually plug in the values would be 4.3 times 10 to the negative 25th times 6.4 times 10 to the 9th. And when you plug that in, it would be 2.8 times 10 to the negative 15th. Okay, now that value is much smaller than 1. So here K is much smaller than 1. So again, keeping in mind what that means in terms of products over reactants, if I think of products over reactants, if this is really small, products has to be a very small, low number, and reactants have to be a very large or a much higher number. Okay, so we would say that this is reactant favored at equilibrium. Okay. All right, so let's say though that we take this reference or this equation number 3 and we look at it in terms of how we're going to get number 4 here. So I can see with 4 that this is just the reverse of this equation. So when I come down here, if I'm looking for the value of Kc4, if it's simply the reverse where I've flipped my reactants and products, I'm going to take the reciprocal of my reference equation in that case. So this would be 1 over Kc3, which then if I actually plug in the values, 1 over the value that I got for number 3, so 2.8 times 10 to the negative 15th. Okay, I'm going to see that my value there is 3.6 times 10 to the 14th. Okay, now if I look at that value for K, K is much greater than 1 here. So if you think about our products over our reactants, to make it that much bigger than 1, our products is going to have to be a very high or large number, and our reactants are going to have to be very, very small or low number in order to produce that value. So in this case, this is showing that this is product favored at equilibrium. Because remember, only rates have to be constant at equilibrium. The amounts of reactants and products do not have to be equal. They just have to become constant. And this should make sense, this relationship between these two. Okay, this was reactant favored up here, meaning we would have more of those reactants in our third equation, which would make sense then that when I flip it, it's now product favored based on the K value. So just something to keep in mind. All right, and then the last little piece we talked about was if we change the coefficients by a common factor, we're going to be taking it and raising it to the exponent of that. So this equation here is based off of our equation 3 again. So I can see that I've multiplied all of my coefficients equally by 3. So if I'm looking for Kc5, this would mean I'm going to take Kc3 and I'm going to raise it to the third power. I'm going to cube it. So if I take my value of 2.8 times 10 to the negative 15th, and I cube it, I get 2.2 times 10 to the negative 44th there. Okay. All right. So you want to be comfortable with manipulating our equilibrium constants using those 3 different possibilities. So this was a question that was on the quizzes where it combines 2 of these. So I wanted to go through it with you. So it was asking for K3 here based on these 2 elementary steps here in their equilibrium constants. So if I look at this, I can see that this bottom equation is used as is, but this equation I would have had to have reversed in order to create this final equation. So when I look at my K3 value, I'm going to have to do the reciprocal of K1, 1 over K1, and then I'm going to use K2 exactly as is. So I'm going to make sure I take the product of the 2 because I'm combining them. And then I'm taking the reciprocal of the first one because I reversed it. So a lot of the times on the AP exam, this is actually what you would be looking for in a multiple choice type of question, is this type of setup. Or they might combine it where you'll see it as K2 over K1. Okay, and that might be your answer if it's not looking for a numerical value. This is the relationship of K3 to K1 and K2. Okay, if you did have to actually plug in the values there, you would go ahead and have your 0.50 divided by our 4.8 times 10 to the negative 31. And when you plug that in, I believe you get 1.0 times 10 to the 30th for K3 there. Okay, so we'll do a little bit more practice with this. I'll give you some questions on AP Classroom as well. So the newer part from today that I wanted to go over is just comparing Q to K and then how we convert between KC and KP. So in this question, and this should have little arrows here, it says if the equilibrium constant for this, and this is KC, is 248, predict if possible what will happen when the reactants and the product are combined at the concentration shown. So essentially these are, think of these as your initial concentrations. Okay, so that means I'm going to be using Q. Okay, and I'm going to use QC based on them being concentrations. So if I set up my equation, I'm going to have the concentration of my product over the concentration of my two reactants. Okay, they all have a coefficient of 1, so they're all raised to the power of 1. I'm simply just going to plug my values in. All right, so when you solve that, you are going to get in your calculator 700. Okay, so what is the importance of that value? So if you think about the fact that 700 is going to be greater than our 248, so Q is greater than K, that's going to tell us which way this reaction has to proceed in order to reach equilibrium. So if you think about, again, this idea of products over reactants, Q has to equal K in order to be at equilibrium. So what must be occurring at this point is that the product value is going to have to decrease overall, and the reactant value is going to have to increase overall in order to make Q smaller and get to K. So in that case, as it approaches equilibrium at this point in time, so at these initial concentrations, the reverse reaction, which is going to consume product and produce reactant, must be going faster than the forward reaction. Now remember, as time continues on and products get consumed and more reactants are getting produced, this is going to actually slow down a little bit, this will speed up a little bit, and eventually they will equal each other. So what this means then is that this system is going to proceed left towards the reactants. Okay, so you might see it just as proceed to the left. You might see it proceed towards the reactants. Either is acceptable here. You could also include in there that, at this point in time, the reverse reaction rate is faster than the forward. Okay, until they become equivalent. This is getting a little out of control. At equilibrium. Okay, so this will become important when we go to do our ICE tables in our next lesson of determining the fact that, again, our products are going to be decreasing and then the reactants amount is going to be increasing. It will help us set up our ICE tables later on. Okay, but you definitely want to go through various questions in the homework on this. All right, last little part here is our KC and KP equation. So in this one, it's giving us our KP value at our specified temperature, and then at the exact same temperature, what is the KC? So this is the equation that we talked about in class. So KP is equal to KC, gas law constant, temperature, raised to the change in moles of the gas state. So one little way to remember this is to always be PC, politically correct, is one way that I've seen to help students remember this, if it helps you remember which goes where. All right, so when we go to plug this in, KP is our 6.5 times 10 to the negative fourth. We're looking for KC. We're going to use the gas law constant that we have been using, so the 0.08206. Okay, make sure that temperature is going to be in Kelvin. Okay, especially based on that gas law constant that has Kelvin in it. And so this is going to be 308. And then I'm going to look at my delta N. So delta N is always going to be the moles of product minus the moles of reactant. So if I look up here, I have 2 moles as my product. And if I look over on my reactant side, I have 2 moles of gas plus 1 mole of gas. We're only doing these for gases. You ignore any solids, liquids, aqueous solutions. This was 3. So when I plug it in here, delta N would be 2 minus 3. So this would be -1. Okay, and if I take my Kp value, I divide it by this value, where you will find that Kc here is 0.017. Okay, so you want to get comfortable with using this and especially figuring out that delta N. Okay, so that is just a recap of what we've done so far in equilibrium. Next lesson, we're moving on to our equilibrium concentrations involving ice tables.